In the world of chemistry, we have so many elements that we need to classify the properly. The question was begun in the year of early 1800 when to a lot of models of periodic table. Coming to the first one is the Dauber triads, and second one is the Newland octaves, and the third one is the Mendeleev periodic table. So these three are purely basing on the idea that the elements are the periodic functions of their atomic masses. Out of the all Mendeleev periodic table considered due to the experimental evidence. In the year 1930, Henry paved a modern periodic law. He was doing the X-ray spectroscopy on different elements. The properties of the elements are function of their atomic numbers. Later, it was notified that protons and neutrons. He used the electronic configuration to fill the elements in the periodic table. While filling the electrons in an atom, if electrons are going in s orbital, those are called as s black elements. If the electron are going in p orbital, that is called as p black elements. Similarly, d orbital, those are called as d black elements, and f orbital, those are called as f black elements. D black elements and F black elements are having multiple oxidation states. P black elements are having metals as well as non-metals. S black elements are having only metals. Coming to the main integrity of this chapter, the first concept is nothing but a shielding effect or screening effect. What happens is in all atom there is the valency electron which is can't feel the full effect of nuclear charge. This is due to there is the certain repulsive force between the inner core of electron with the valency of electrons. So mathematically we can say that the charge is directly proportional to the atomic number, and the charge faced by outermost electron is called as effective nuclear charge, which was written as Z equal to Z minus sigma. Sigma is nothing but a shielding effect. Shielding effect is more in case of s orbital. In case of p orbital, we can observe the low screening. In case of d orbital, we can observe a very low screening effect. So in case of f orbital, there is no screening effect. While talking from the general trend of nuclear charge, as we go from left to right in the periodic table, the nuclear charge is completely increasing, and then came to the idea of atomic radius. So atomic radius means the distance from the center of the nucleus to the outermost electron, that is called as atomic radius. But in old days there is no accurate method for measuring of this. They used different techniques. What they did is covalent radius. So covalent radius is defined as the half of the distance between the one nucleus to the another nucleus in the covalent bonded between the two metals. So those are called as covalent radius. So similarly, in case of metallic radius, we can measure the half of the distance between the nucleus between the two metals. In case of van der Waals radius, we can measure the distance by taking the noble gas in the solid form. So in these three kinds of the radius, van der Waals radius is more as compared to the metallic, and covalent radius is less as compared to the metallic. So out of the three radius, van der Waals radius is more as compared to the metallic and covalent radius. So while talking about general trend of atoms, general trend of atomic radius, from left to right it was decreasing, and from top to bottom it was increasing. Coming to the isoelectronic species, the one which is having the less amount of the proton will have the more atomic radius, that is called as isoelectronic species. We have the number of the examples, and also you know the number of values also. Let's talk about ionization enthalpy. Ionization enthalpy is referred as the energy which is required to remove the electron from the outermost shell known as ionization enthalpy. So there are number of ionization enthalpies. One is the first ionization enthalpy, and next one is the second ionization enthalpy, and third, fourth. So we can continue as much you want. First ionization enthalpy is defined as the energy which is required to remove the first electron from the outermost shell, known as first ionization enthalpy. The second ionization enthalpy is nothing but the energy which is required to remove the second most loosely bounded electron from the valence shell, that is called as the second ionization enthalpy. The values of ionization enthalpies are always positive, because we have to give some positive charge in the charge. So this is the graph we are observing. In between the beryllium and boron, nitrogen and oxygen, and magnesium and aluminum, finally phosphorus and sulfur, there is the anomalies of ionization enthalpies. This is nothing but, in case of beryllium and magnesium, we can observe the fully filled electrons, and in case of nitrogen and phosphorus, we can observe the half filled orbitals. This is that they are slightly stable than the expected, so they show the little more ionization enthalpies. Next one is electron gain enthalpies. The electron gain enthalpy can be defined as the energy which is released by the addition of extra electron, known as electron gain enthalpy. Mathematically, electron gain enthalpy is always the positive values. So we have to convert the atom into the ion for noble gases. The values are always positive values. In case of halogens and chalcogens, the electron gain enthalpy values are always with negative sign. And next one is the electron affinity. Electron gain enthalpy and electron affinity both are completely same. Mathematically both are completely same definition. But when we observe the values, chlorine is having the electron gain enthalpy minus 350 kilojoules per mole. But chlorine is having the electron affinity, that is nothing but 350 kilojoules per mole. Both are having same, but the signs are purely different. But there is a exception in case of oxygen, fluorine, sulfur and chlorine. What is the reason is nothing but, in case of oxygen and fluorine, so oxygen and fluorine atoms are small as compared to the others. So whenever extra electron is added to the oxygen and fluorine, automatically that added electron can face a lot of repulsion. So we can observe the different values. Right now there is the trend of electron enthalpy. As we notice that halogens are at the top of the graph, and nitrogen, phosphorus, magnesium, beryllium, zinc are at the bottom. This is due to the nitrogen and phosphorus are having half filled orbitals, beryllium and magnesium is having fully filled orbitals, and zinc is having pseudo noble gas configuration. That means it does not want to change its configuration. So while talking about the general trend, as we move from left to right, the electron affinity values are completely increasing, and as we move from up to down, the values are completely decreasing together. And the next one is electronegativity value. So the electronegativity is defined as the property of the ability of atom to attract the shared pair of electron, which is called as electronegativity. The value of electronegativity is not used for particular atom. It is purely depending upon the element which they combine with another metal. Linus Pauling is the scientist who gave the table which represent the electronegative values of different elements. Okay, this is the table which is showing the electronegative values of different elements. So out of the all elements, fluorine is having the highest electronegative value, that is nothing but 4.0. Coming to the general trend of the periodic property, as we move from left to right, the electronegative values are somehow increasing. As we move from down, the electronegative values are completely decreasing. In case of the fluorine, we are observing the value 4.0. So when we observe the group of halogens for the fluorine, we have 4.0, and for chlorine we have 3.0. In case of the bromine, we have observed that there is the 2.8. So in this way, all the electronegative values are purely decreasing together. And coming to the metallic characters of oxides and hydroxides. So metallic oxides and hydroxides are purely basic in nature, so we call them as alkali metals, as well as alkaline earth metals. Non-metals are purely acidic in nature. Metalloids, which are present at the middle of the periodic table, are purely amphoteric in nature. And next one is the covalent character. Whenever the two elements will be combined together, the electronegative difference is more than 1.7. That kind of the compounds are called as ionic compound. The best example of ionic compound is nothing but sodium fluoride. So when the electronegative difference is less than 1.7, that compound is called as a polar covalent compound. The best example is water molecule. And whenever the electronegative difference is equal to 0, that means there is no difference, that compound is called as a pure covalent compound. The best example is H2 or water molecule. Now there is the slight difference between the three kinds of the values. These values are more helpful for the final examinations. Now this is the chart which is purely representing the general trend of the periodic properties. Now in case of ionization energy, in case of electron affinity values, so as we move from left to right, ionization energy values as well as electron affinity values are completely increases. And in case of atomic radius, as we move from down or in groups, the atomic radius value is completely decreasing, and electron affinity values are completely increasing. This is the chart which is representing the periodic properties of number of metals. Now this is the summary of all trends of periodic table, which will give you a lot of information which is suitable for the revision program of your final examinations. This video